Hello, everyone. Good afternoon. Dear authors and invited guests, welcome to Technical Session 6C. I'm Pranjal Bange, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Conference on Information and Communications Technology for Sustainable Development, ICT4SD 2026 in Goa, India. The 11th edition of the conference is being organized in a hybrid mode. The physical event is being held today, that is 9th July 2026, in Goa, India, and the virtual event is being held through Zoom from 9th July to 11th July 2026. I hope you'll enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 10 presentations. Each presenter will be given 10 minutes for the presentations and 2 minutes for questions and answers. In 8 minutes, I'll raise a gentle reminder. There's another request to all the participants that you all stay connected with us till the closing remarks. Now, if you have any queries or updates, you can write it to me or to my co host in the chat box. Before we start the session, I would like to introduce our session chair for this session. Professor Kirit Modi is the professor and director of Head IQAC, Amity University, Noida, India, with over 25 years of teaching experience. He has published more than 50 research papers in reputed international conferences and journals. His expertise spans artificial intelligence, cybersecurity, cloud computing, IoT edge computing, fog computing, and big data analytics. Sir, would you please like to deliver some opening remarks? Kirit, sir? Now, moving on, I would like to start with the presentations. I would like to call upon Shiva Karthik to present his paper on a hybrid LLM plus rule based system for mapping protest events to timelines from Indian language noisy web data. You may start with your presentation.
Hello, ma'am. Am I audible?
Yes, sir, you're audible.
Yes, so this is Rajat Srivastav. Srivastava, actually, he is on a office tour, so I'll be presenting on behalf of him.
Okay, sir, you
Yeah,
may start your presentation.
sure. Is my screen visible?
Yes, your screen is visible.
Thank you, ma'am. So, good afternoon, everyone. I'm here to present on the topic a hybrid LLM plus rule-based system for mapping protest events to timelines from Indian language noisy web data. So, the idea is combining LLM semantic extraction with deterministic temporal grounding for English and other 9 languages. So myself, Rajat Srivastav, I'll be presenting. So let's carry on. Let's dive in. So first, why there is a need to present this topic? Basically, as we all know that the web data is quite loud, so there is a lot of data that has code mixed informal languages, like the data that is published on web, on social media, and even in the news articles that we see, that it is often mixed with informal language. So this is the first challenge that we face. Second is missing and unreliable metadata. So in many of the data that gets published or that gets crawled, uh, there is a missing unreliable metadata, which means the publication dates of when an article has been published is more often missed in tens of thousands of documents. And the third challenge that we face is vague temporal references. That means there are references in the post published by users, like yesterday, next Monday, or this week. In that case, we find it difficult to map those events to the date. We don't know the exact date. So one such real example of what we are trying to achieve here is given over here, where the event is silent rally and procession by ABC Society residents, and the date it is given. So why does this matter? Why we are doing this is the structured event timelines power applications in social search, media analysis, and crisis monitoring. So mapping protest-related events to proper dates help us analyze when the protests will be happening and then take actions accordingly. So there are existing approaches, and I would like to discuss why they fall short. There are two approaches using which we can do this. The first one is LLM based, and the second is rule based. So in LLM based, as there is a strong zero or few shot semantic recognition. What this means is LLM is capable of reading a sentence and then identifying the event and the date it when it will be. But it has some disadvantage or some limitations, that there are hallucinations and temporal drift in LLM. Like if the article published date, or if the published date is not mentioned with the article, LLMs might find it difficult to find the exact date when the event is going to happen. And the other limitation is no schema adherence. So as we all know, LLMs mostly they give free form output, and it can break structured pipelines. The second approach is rule based, where we do achieve high precision in identifying the events. However, it gets limited into other language data. Like if there are, uh, like we have data in multiple languages, there we may find it difficult for rule-based approach to identify the events because of the Indian language morphology and code mixing. Also, it cannot handle missing metadata. LLM has the capability to uh, to adjust with the dates like yesterday, or resolve it and map it to event. However, in rule based approach we cannot do that. So there is a gap where when the data is Indian languages plus the noisy data. As we all know, the English benchmark data sets are available. They are centric and clean, but the challenges that we face are on Indian language data, which are morphologically rich and code mixed. So that is why we are going to use a hybrid approach, which is LLM plus rule based approach to serve the purpose. So the three things that we deliver in this is the modular hybrid pipeline for noisy web crawls. In this modular hybrid pipeline, we have 5 stages, right from the crawling to the mapping the data on the calendar. We extract entities, temporal grounding, and calendar construction, which is tested on English plus 9 Indian languages. Second contribution is uh, temporal inference strategy for relative dates. So if in the article that there are dates which are mentioned like yesterday, this Monday, then using the published date of article, we can map these events on the calendar. And the third contribution is ethical comparable evaluation and ethical discussion. So we have benchmarks using which we have tested and got results, which also includes 95% confidence intervals that we'll discuss ahead. So this is the related work what the field has built so far. The first is supervised event extraction, which is based on clean news data, and but on open web it has limitations. The next is NER, wiki events, and LLMs. Are LLMs ready? So LLMs, as I told, they have strong semantic extraction, but because of hallucinations and temporal drift, it motivates the hybrid that we propose. So this is the 5 stage pipeline, right from crawling to mapping the data on the calendar. The first step, we do the web mining, which has the data from national and local news portals, blogs, and community sites. Then we clean and dedupe, where we do the operations like template removal, deduplication, language filter, and sentence segmentations. Also, we manually annotate the data based on events and their dates. Next, here the LLM role comes into the picture. We use LLM prompts for identifying the person, organization, location, dates, and event, basically NER, and we return the data in JSON format. The rule-based approach comes into picture in temporal grounding and event date mapping, where we resolve the relative dates present and the events that are extracted by the LLM with the help of article published dates that are present in the article. And the final step is mapping those event dates into the calendar. Next, these are the prompt templates that we have used. The first step is NER, named entity and event and extractions, and where we have strictly returned the data in the JSON format. Next step is event date mapping. Next is multilingual normalization. Since the data we have in multiple Indian languages, we first use LLM to extract those events, and then we translate those events to English language and normalize it to strict date format. Uh, Next is disambiguation and schema validation. So here's the worked example of thousands march last Friday in downtown Cairo, where the event is about the march and date is extracted. And the next example in Hindi shows silent rally and procession by ABC Society residents, and the date is also extracted.
I'm so sorry to interrupt, but I'd now request you to conclude your presentation.
All right, ma'am. So based on we have achieved these results based on our approach, the hybrid approach. As we can see, the precision and recall in rule based is lesser, whereas in LLM the recall gets more. That is, the LLM can add its own data sometimes. The hybrid approach is where we find the best balance and the good precision and recall, and hence the F1 score. So this is robust across all languages. These are the results. These are the date event mapping accuracy and event detection accuracy for different languages. English, since we have the clean data and LLMs are more trained over English language, we have high accuracy, but it performs relatively well in Indian languages as well. So the key takeaway that we have is we combine LLM semantic extraction with rule-based temporal grounding to map protest events from noisy data across 10 Indian languages, and we have achieved an F1 score of 0.79 with 0.83 date normalization accuracy. So what still hurts is that the limitations that we have is the data. We are highly dependent on article date, so that is the one limitation, that we would need article dates to map the events ideally. So the next steps that we are going to do now, we usually do batch processing, but now we are looking and we are working on real-time ingestion and human in the loop validation. Thank you.
Thank you so much. I would now like to ask if the session chair has any questions. It seems that is not the case, so we'll be moving forward with our next presentator. I'd like to request Prisha Priya to present her paper on attack resilient differential privacy enhanced federated learning for multi center polyp segmentation. You may start by presenting your screen.
Good afternoon. I'll
Good
just
afternoon.
share my screen. Good afternoon, everyone. I am Prisha Priya, and I'll be presenting our project on the topic Attack Resilient Differential Privacy Enhanced Federated Learning for Multi-Center Polyp Segmentation. My co-authors are Anusha Jain and Shaira Vadar. Colorectal cancer is one of the leading causes of cancer-related deaths across the world, and the survival rates can be improved by early polyp detection during colonoscopy. Deep learning, especially UNIT, has shown impressive results in medical image segmentation using colonoscopy. But one of the biggest challenges remain the requirement of large data set required, and sharing medical images is restricted by patient privacy regulations and ethical concerns. Federated learning enables collaborative model training without sharing raw medical data. Although federated learning prevents sharing of raw patient data, model updates can still leak sensitive information. This vulnerability is exploited by two very important attacks. First being the membership influence attack, and the second is gradient leakage attack. Differential privacy can be integrated into federated learning to mitigate information leakage using gradient clipping and Gaussian noise. Uh, we have aimed uh, developing at improving the privacy while still keeping the segmentation accuracy practical. This diagram represents the workflow. Every client trades locally with its own local data, and the trained parameters are shared into the global model, which are aggregated into a global server. In the case of differential privacy, the gradients are clipped and Gaussian noise is added before actually sending the updates into the global model. We have evaluated three training paradigms for comparison: centralized learning, federated learning, and federated learning with differential privacy. The figure here shows the overall system architecture of the proposed framework. Federated learning will have 5 non-IID healthcare clients, where the polygen data remains local to each client, and differential privacy is implemented using DPSGD, which is applied before training to implement gradient clipping and Gaussian noise before actually sharing the updates to the global model. For segmentation, we have used a lightweight UNet architecture. UNet is particularly useful for medical image segmentation because encoder captures the higher level contextual information, and decoder reconstructs detailed segmentation masks. Skip connections preserves the spatial information that would otherwise be lost during downsampling, allowing accurate localization of even the small problems. We have used group normalization instead of batch normalization because it provides more stable training with relatively small batch sizes, which are commonly used in medical imaging. And finally, we have optimized using a hybrid loss function of dice score and binary cross entropy. The dataset that we have used is a PolybGen dataset consisting of more than 2,200 annotated colonoscopy images collected from 6 medical centers across 3 countries. The dataset has a diverse set of images collected from different endoscopic devices with different light settings, which offers a diverse imaging set. And each image is pre-processed by resizing, normalization, as well as augmentation, which includes flipping, rotation, brightness, and contrast adjustment. The image over here is an example of one of the training samples. One of the privacy frameworks that we have used is federated learning, which trains where the clients train locally using their own local data sets, and only the updated model parameters are shared with the global model. Fed average aggregates the model parameters based on the data set size. Another privacy framework here is differential privacy. Federated learning, although ensures certain privacy levels, it does not eliminate the risk of privacy attacks, and therefore, differential privacy is implemented using DPSGD, which uses per sample gradient clipping and adds Gaussian noise. Gradient clipping ensures that one particular sample does not influence the model excessively, whereas Gaussian noise is added to introduce randomness into the parameters that are shared to eliminate the amount of information leak risk. These help defend membership influence attack and gradient leakage attack. Coming to membership influence attack, This attack exploits the model memorization of training samples. It works on the principle that member samples generally produce lower loss values than non-members. So if the loss gap between the member samples and the non-member samples is large, the attacker will easily be able to differentiate between the data samples of a training set and a non-training set. The gradient leakage attack or the reconstruction attack is a much more dangerous attack which attempts to reconstruct sensitive training images from shared gradients. We have used a DLG-based reconstruction method. We start with a dummy image which consists of random Gaussian noise, and it is optimized until the generated gradients match the observed gradient. The experimental setup is implemented using lightweight unit with PyTorch. Federated learning setup includes 5 simulated non-IID clients, and the training takes place with 2 local epochs per round and 50 communication rounds in total. Differential privacy is implemented using DPSGD with gradient clipping of 1, Gaussian noise multiplier of 1.5, and privacy budget of 3. Moving on to the results, we'll start with the segmentation performance results, where centralized learning and federated learning show comparable results. Centralized learning showing a DICE score of 0.8936, while federated learning a DICE score of 0.8949. Federated learning, along with differential privacy, shows a slight performance drop with DICE score of 0.8593. Although there is a slight performance drop, DP plus FL still maintains clinically acceptable segmentation performance. Looking at the privacy robustness results, we first assess the membership inference attack, where federated learning alone shows the highest attack success rate and highest attack accuracy, indicating that federated learning alone is not enough to prevent privacy attacks. Whereas FL plus DP shows much reduced attack accuracy in ROC AUC, which is very close to random guessing. These graphs show what the numbers were telling graphically. The first graph is showing the loss gap, which is the highest in the case of federated learning and much less in the case of federated learning plus DP. Second graph shows privacy budget, where the privacy budget is set 3. Privacy budget tells how much privacy leakage is allowed in a system, which is the lowest in the case of FL plus DP. And figure 9 represents comparison of MIA metrics, attack accuracy, ROC AUC, and loss gap across the 3 training paradigms. Gradient leakage attack, this shows the visual results of a gradient leakage attack. In the case of centralized learning, the reconstructed image retains substantial anatomical details, whereas in the case of standard federated learning, there's still structural information that is being retained in the reconstructed image. In the case of FL plus DP, however, we see that the reconstructed image is basically random noise and no anatomical information is being retained or leaked in that case. So this clearly represents that reconstruction attacks are prevented using by integrating differential privacy into federated learning. To conclude, we have developed a DP enhanced federated learning framework for multi-center polyp segmentation, and federated learning has demonstrated to achieve a performance very close to centralized learning despite non-IID data and localization. Differential privacy has improved protection against privacy leakage with a moderate accuracy trade-off. Our aim was to maximize privacy while still keeping segmentation accuracy practical. For future work, we aim on working on adaptive differential privacy, personalized federated learning, using FedBN and FedProx, secure aggregation, and working on a much larger multi-center dataset. Thank you. I'll be happy to answer any questions.
Thank you so much, Prisha, for such a wonderful presentation. The session chair, sir, do you have any questions for her? It seems he doesn't have any questions, so we'll be moving forward to our next participant, Divya Bharti. I would request her to present her paper on comparative analysis of classical machine learning and custom CNN model for brain tumor detection and classification. You may start your presentation.
Hi, good afternoon.
Hello.
Hope my screen is visible right now.
Yes, Divya, your screen is visible.
Yeah, thank you. So, good afternoon, everyone. I'm Divya Bharati, and I'm presenting our work on comparative analysis of classical machine learning and custom CNN models for brain tumor detection and classification. So, this study asks a focused question. For brain MRI classification, do handcrafted feature-based classical models still hold up, or does a custom CNN performs better when both are tested fairly on the same database? So, before getting into the brain tumor classification and the models which we have used for this study, I would like to talk about brain tumor in general. So, currently, all around the world, about 7 lakh people are living with primary brain tumor, and about 87,000 people are new cases are diagnosed annually in United States alone. So the motivation for this study is straightforward. If machine learning can classify MRI scans more consistently and accurately, it can support radiologists in a setting where speed, reliability, and early decision making matter. So, a lot of prior work evaluates either classical machine learning or deep learning in isolation, often on different data sets and different pre-processing pipelines. So, our objective was to build a controlled benchmarking framework and compare four classical machine learning models against a custom CNN under the same dataset, same pre-processing, and same evaluation metrics. That way, the performance gap we observe is meaningful and directly interpretable. We used a Kaggle brain MRI dataset with four classes: glioma, meningioma, pituitary tumor, and node tumor et al. Even though there are over 120 types of brain tumors classified all around the world so far, we have chosen these four classes alone and three very popular cases of brain tumors, so that it will be more concise and the results will be more accurate. So after cleaning the data, which has been done through a very strict data quality pipeline, starting with OpenCV validation, where we have checked all the images for any corruptions, and followed by an MD5 hashing algorithm duplicate removal, where we removed 218 duplicates, which was about 3.8 percentage of the entire data, and finally a standardization procedure where all the images were resized into 128 cross 128, and they were converted into grayscale. After all these cleaning procedures, the final data set contained 3,264 MRI images. An important part of the study was data quality, because in medical imaging, model performance is only as trustworthy as the data set behind it. So, this is how the methodology works. First, the raw data set was uh, pre-processed. So before training, we applied pre-processing and validation pipeline, uh, where we removed 218 duplicate images, then resized them all and normalized them to the 0 to 1 range. So was a very important step. So after all these pre-processing, the pipeline was split into two modeling tracks. The first track, the track one, is classical machine learning. For this branch, we extracted HOG, which is histograms of oriented gradient features, from each MRI image and used them to train four classical machine learning algorithms like SVM, random forest, KNN, and logistic regression. And as far as the track two, which is deep learning, in parallel, we trained a custom CNN directly on the MRI images. So the comparison is essentially between an handcrafted feature extraction plus classification versus end-to-end learned feature extraction through CNNs. For the classical model, feature extraction was done using histogram of oriented gradients, or the HOG, which captures structural image information such as the edges, gradients, and local texture patterns, which are relevant in MRI-based tumor classification. These HOG descriptors were then used as input to the four classical classifiers or the classical ML algorithms, allowing us to test how far an handcrafted feature pipeline can go before deep learning becomes a necessity. So, among the classical models, logistic regression was the one which performed the best with 94% accuracy, followed by SVM, which is support vector machine, which had an accuracy of 93.2%, followed by random forest at 90.7% accuracy, and at last KNN, the K nearest neighbor algorithm, at 88.6% accuracy. This is an important finding because it shows that classical machine learning is still highly competitive when combined with strong feature extractor like HOG. So even before the CNN is considered, the base pipeline, actually the baseline, the classical machine learning algorithm performance is already quite strong. Now, coming to the deep learning branch, we designed a custom CNN with three convolutional blocks, followed by batch normalization, max pooling, dropout, and a softmax output layer. We call it custom because it is not a pre-trained architecture like ResNet or VGG. It was built specifically for this four class MRI classification task. Its advantage is that it learns features directly from the image instead of depending on manually designed descriptor. So the custom CNN achieved the best overall performance with 97.4% accuracy and 97.3% weighted F1 score. And here we have described the final ranking as well, with custom CNN ranking the highest and KNN, the K nearest neighbor algorithm, ranking the lowest. This tells us that while classical model remains strong, CNN gives a clear performance advantage under the same experimental conditions. Okay. So the biggest challenges in the classification task was distinguishing between glioma and meningioma because these classes can share overlapping MRI characteristic. Glioma is basically tumor in the glial cells, and meningioma is tumor in meninges. So when both of these are seen through an MRI image, they share fairly similar features. So it is hard to distinguish the both. So the CNN handled this better than the classical model, which suggests that learned hierarchical features are more effective than the HOG descriptor when the boundaries are very subtle and hard to clearly differentiate. So the takeaway is not just that CNN scored better or it had more accuracy rate, but the importance of this study lies behind the reason on why it scored better. So at the same time, based on this study, based on this paper, we are not suggesting that classical machine learning is obsolete. In fact, logistic regression at 94% and SVM at 93.2% are actually strong results. But it all depends on whatever the situation we are using it. That's why we are suggesting a tiered deployment strategy where high stakes clinical setting like big corporate, big hospitals are places where this kind of GPU interface infrastructure is available or can be afforded, they can go for the CNN and so especially places where maximizing the diagnostic accuracy is very critical, they can opt for CNN. At the same time, places where
I'm so
deploying
sorry to
such,
interrupt,
yeah,
but now I'd request you to conclude your session. Your
yeah,
time is up.
sure, ma'am. So, what I'm saying is, both logistic regression and SPM have crossed the 93% accuracy rate, which is a good indicator. So, we are not suggesting one is better over the other, but it's just a comparative statement. So, to conclude, we compared four HOG-based classical machine learning model with a custom CNN for four class brain tumor MRI classification on a clean data set of 3,264 images. The results showed that classical model are still strong, particularly logistic regression, but the custom CNN performs overall better. If I had to summarize the study in one line, I would say when brain tumor MRI classification is evaluated fairly, classical machine learning remains strong, but a well-designed CNN goes further. So thank you, and I look forward to your questions.
Thank you, Divya, for such an immaculate presentation. Now, I'd like to move on. I would now invite Noshin Razanias to present his paper on dielectric modulated double dual material gate TFET with engineered end pocket for detection of breast cancer cell. You may start your presentation.
Hi, yeah, let me just share my screen. Is my screen visible? Hello?
Yes, your screen is visible.
Hi. So good afternoon, everyone. My name is Noshan Raza, and I'm representing Delhi Technological University Electronics and Communication Department. I'm proud to present our research titled Dielectric Modulated Double Dual Material Gate Tunnel FET with engineered end pocket for detection of brain cancer cells. So this work was co-authored by my colleagues Akash, John Varghese, and Riddhi Tandon, and supervised by Dr. Sumit Kaile. Our research introduces a highly sensitive ultra-low power biosensor designed to detect breast cancer at the cellular level, leveraging advanced semiconductor engineering to address the urgent need for accessible diagnostics. So to understand the motivation behind this work, we must recognize that the breast cancer remains one of the leading causes of female mortality worldwide. Conventional diagnostic methods like mammography, MRI, and tissue biopsies are essential, but they are often invasive and time consuming. So there is a critical gap. We urgently need to point of care diagnostic tools that are affordable, label free, sensitive, and easily miniaturized for resources limited. So to transition into the motivation, this brings us to the dielectric modulated tunnel FET. They are inherently advantageous because they operate in the subthreshold tunneling regime. They utilize band-to-band tunneling, allowing them to overcome the Boltzmann thermal limit. This enables ultra-low power operation. Furthermore, they're extremely sensitive to variations in gate capacitance. However, prior tunnel FET biosensors have struggled with limited ion sensitivity, which is typically below 2.5 into 10 raised to the power 2, and the threshold voltage sensitive below 66 millivolt, making it difficult to clearly distinguish between different breast cancer cell lines. So our goal was to push these boundaries. So to achieve this, we proposed a novel architecture, the double dual gate material tunnel FET. It was built on a 10 nanometer thick silicon body with a 100 nanometer channel length. Our design is the first to integrate three specific engineering techniques simultaneously, which are the double dual material gate. So we use tunnel gate with a work function of 3.9 electrovolt over the drain side channel and an auxiliary gate at 4.5 electrovolt over the source side. We also introduced engineered N pocket, which was heavily daubed N pocket at 10 raised to 19, right at the source channel interface. This sharpens the band structure, intensifying the local electric field to enhance the tunneling rate without degrading the leakage current. We also applied low K silicon iron oxide over the source and high K HFO2 over the drain end. An nanocavity is then etched into the gate. dielectric near the tunnel junction. So when breast cancer cells are immobilized in this nanocavity, the distinct permittives alter the effective dielectric constant of the gate stack. So see this to see the simulation setup and the cell lines. Our simulations were conducted using Silvaco Atlas 2D Drift Diffusion Simulator. So we utilized rigorous physical models including Fermi-Dirac statistics, band gap narrowing, and non-local BTBT with lateral quantum tunneling. To ensure physical accuracy for a thin body geometry, we validated this framework by reproducing experimental transfer characteristics from previously reported dual material T-FET biosensors, which was achieving close agreement. So we evaluated our sensors across a baseline air of K is equal to 1 and four distinct biological state, which is MCF10A, HS57AT, MDA MB231, which all possesses different permittivity, and T47D, which possesses the highest permittivity at K is equal to 32. So to see the performance across all the N channels, a core focus of a study was optimizing the width of the N pocket. So we simulated widths of 2, 4, 6, and 8 nanometer. So for the 2 and 4 nanometer, we observed a clear leftward shift in the threshold voltage as permittivity increased from air to the T47D. However, the separation between the closely related HS5780 and MDA cell lines were narrowly related. So at the extreme 8 and pocket yielded an exceptional subthreshold swing of 45 millivolt and a peak transconductance of 1.3 into 10 raised to minus 5. But it also unfortunately pushed the threshold voltage to 1.35 as mentioned here, which would require a higher supply voltage and undermine our low power objectives for point of care devices. So then we transitioned to the optimal design, which led to a 6 nanometer pocket configuration, which provided the perfect balance. So in this configuration, we achieved an on-state current of roughly 1.05 into 10 raised to minus 5 for the 347D line, maintaining a steep subthreshold swing of 55 millivolt. The off-state leakage remained incredibly stable near 10 raised to minus 11 as. And most importantly, all 5 cells were distinctly spread across the full voltage range. So to benchmark the sensitivity, when we benchmark this optimized 6 nanometer design against the current state of the art DFET, the synergistic effect of a three design pillar becomes evident. We were able to achieve ion sensitivity of 2.74 into 10 raised to 2. This is a 9.6% improvement over the best prior metric reported by Kumar and Kale. Even more significantly, we achieved a threshold voltage of BTH of 135 millivolt for the T47D cells, which is related to the air baseline, and this represents a massive 104 percentage improvement over the 66 millivolt baseline established by Narangal, effectively doubling the sensing resolution for these cancer cells. So see the fabrication feasibility. While these simulation results are highly promising, we must acknowledge that the physical fabrication process, the dual dielectric stack, can be reliably realized using atomic layer deposition for monolayer thickness control. However, the primary manufacturing challenge remains the formation of the sub 10 nanopocket with a sharp doping profile. So conventional ion implantation suffers from straggling effects at this scale, suggesting that in STU, we will be requiring for experimental realization. So to conclude our study demonstrates that integrating a dual material gate, a dual electric stack, and an engineered end pocket creates a highly sensitive, energy efficient biosensor. The optimized 6 nanometer configuration reliably differentiates between multiple breast cancer cells, surpassing prior designs by nearly doubling threshold voltage sensitivity. Because this is currently a simulation based study, our vital next steps involve physical fabrication to validate these metrics against real world variables like thermal noise and interference trap states. So, thank you for your time and attention. I'm now open to any questions.
Thank you so much for your presentation. It seems there are no questions, so we'll be moving forward. I would now like to invite Somasi Pathania to present her paper on evaluating Fed average and Fed adgrad in privacy preserving federated image forensics across IID and non IID data settings. You may start with your presentation. It seems Miss Somasi isn't here, so we'll be moving forward to our next presentator. Just a minute. For the next presentation, I would like to call upon Krishnamurthy sir to present his paper on Hybrid Quantum Classical Learning Framework for Accelerated Big Data Interference on Edge Devices. So you may start with your presentation.
Yes, my screen is visible.
Yes, sir, your screen is visible.
Yeah, thank you very much. And now I'm going to present as an hybrid quantum classic learning framework for accelerated big data interface of edge devices. Actually, this is one of the major challenges nowadays. Why? Because it's big data interfaces, the data collection and then data loss. So these all are the major issues. So that we have overcome with the edge devices as well as the interference traffics. So I come to propose one. And, my major objective is for an classic learning frameworks with the aim of accelerating big data interface. And then I can use this hybrid things. What are the hybrid models? The hybrid models we are using is mobile net and then tree-based embeddings as well as then PQC and QPC. Because it's in variational quantum as well as in the quantum processing. This too is a major role for overcoming the interferences. As well as the traditional models, we go for the quantum. In the quantum, they have a lot of security issues. As well, we go for an hybrid quantum, which is more secure than compared to the traditionals. And then come to our introductions. Now, we are using as an internet because no internet without internet they are not working anywhere because it's now the upgrading go for an mobile networks through the IoT. We can use some of the intelligent sensors to create more data and the edge networks to use it to again know the signal to use this some of wearable devices as well as we go for an lightweight devices because in this we want an latency is a less latency. Why? Because we go for an higher fast rate so that we go for a less latency as well. The bandwidth restrictions, there's so many. These are the thing, the major issues. I give you some of big data inferences. It uses big data inferences of edge data to use as a power efficiency, low latency, cost effective, reliable. Because these are all the things is come under the mobile privacies. So these mobile privacies to use it to and secure of big data inference. And our proposed methodology is used to the hybrid learning frameworks, is used within the data architectures and the compromising of the quantum and the classical calculations. Because of the sum of limited edge devices. In this architecture, as a four primary layers, it's a name like data acquisition, pre-processing, classical inferences, and quantum enhancement. So these are the things used as the set of IoT with the edge sensors They capture their large data streams and then high valuations like as a temperature prediction, machine operations, and biometric measure. This also comes under the input of data. And we go for an denoised normalization using as a formats. The three layers to use as a tree-based models are used for gradation boosters and addition trees. See, this is the workflow of hybrid quantum. We use as a layer architecture, and the layer architectures to as a classical inference and a preprocessing model to as integrated model, and then we go for an edge. In intermediate, you can use as an quantum maintenance as well as the delay. So this is one of the workflow, and then how the data will partitioning and pre-processing of the pipelines, because it's a handling a big data in the edge device is using as a pre-process approaches, because of the data will be comes from under first in and first order concept. You can use it to measure the data. So which one is the first to an local recognition models to use to impute of missing values as well as the real-time data. And hybrid optimization. Here, the hybrid optimization is one of the order to support us, uniformity and functionality of the data models of the edges, and is a combination of the two classical and quantum subsequently for ensemble techniques to use as a weightage for schemes. And okay, I come to result and discuss. I did so many works related to this. I will show in the graph. This is accuracy comparison. We worked on that, and how the vibration age, IoT, and temperature deep ECG classification, smart energy, motor sensor, pressure sensor, urban sound and air quality, and wearable. So these are all the things I worked with, and then it's moreover our works. That means in the more of accuracy is in more high to compare it to the previous works, because the classical one, the classical model is nothing but is a traditional model, and then quantum model is there implemented. In our purpose is an hybrid model. The hybrid model is achieves more than these two, because it's, it's in more accuracy comparative in the traditional as well as the quantum. Because it's a 90 plus there are achievements. The violet color, see the graph, the violet color is a more efficiency for us. Come to our power consumptions. The power consumption is also one of the major factors they're using in the hybrid model. You can see this, and in this hybrid model is a more efficient for the power consuming. Because if you go for an quantum model, the power consumption is more high compared to the traditional ones. But in hybrid models, the classical model and quantum model, it will be in less compared to the quantum model. But as the classic model, the power consumption is very, very less, but not in the efficiency. So that we go for the hybrid models. And this is also entropy based prediction accuracy. This is also one of the accuracy can the gained accuracy. There is also one of big achieved in our work. And I come to our conclusions. So one of the hybrid module is accuracy is 94.5 percentage is an accurate, and then false negative predictions. I have investigated to false negative predictions, because no one can go for a false negative, but in our things we go for an identified as a false negative of 14.6. So this will be platforms is workers and so many things, but in our systems is used to in the Raspberry Pi and design and the Arduino, like the small devices, you can small local devices. So these are our references, and then thank you. I'm expecting the questions from our side.
Thank you so much, sir, for your presentation. And it seems like we have no further questions. Then I'd
Thank you.
like to invite our next speaker, Syed Samir Ali, to present his paper on judging artificial intelligence in code performance. You may start with your presentation.
Good afternoon, everyone. Uh, is my screen shareable, ma'am?
No, sir, your screen is not visible as of yet. Yeah, now we can see your screen.
Is it visible now?
Yes, it's visible now. You may start.
Okay. Good afternoon, everyone. My research topic is judging artificial intelligence in code performance, and authors are myself, Sayed Samir Ali, under the guidance of Dr. Animesh Kumar Agrawal from Karnavati University. My contents include overview, problem formulation, research objective, literature review, data description, research methodology, techniques used, case study taken, research findings, and references. Overview. As we know, currently India is having a large volume of pending cases, nearly approximate to 5 crore pending cases. So, judicial technological reforms with the use of artificial intelligence is very much needed for the upgradation of the current system of judicial governance. The integration of the AI models and algorithms must be used in judicial system is the need of hour for the important evolution in how the court operates and delivers justice. Also, the black box approach of modern machine learning models must be taken into consideration, which poses a great challenge for judicial accountability and transparency. Problem formulation. As I told, Indian judicial system is facing a tough situation with a massive backlog of cases, uh, leading to slow justice and drop in public confidence. The old ways of managing the cases aren't sufficient. So we must use AI for effectively solving these cases in a transparent and more effective way. By automating the administrative task, organizing cases effectively, and giving judges real time legal insights can enhance the process. So, objectives include building a framework for incorporating AI tools into the judicial decision making process, which lead to faster and more accurate assessment of the legal precedents and case details. Furthermore, investigation of how AI implementation can help in reducing the delays in court processes, particularly for cases that tends to high volume or repetitive, which means that took very large time. Research tries to bring out the effects of usage of AI in court performances. Literature review, we can see research around the world is being done in this area. Samir Patil and D. Desai used advanced case prioritization algorithms for the uh, pendency reduction, but research gap in that is the real world validation is absent. The results of that research is that 20% decline in overall case backlogs and time duration is also decreased by 35%. In 2025, junior and other researchers include and an online dispute resolution method for the smooth conflict resolution. But they also lack validation and legal domain coverage has been limited. In 2024, research has been done by J. Pereira and other researchers include LLM models for streamlining the case inspection phases. But gap include evolution of the LLM in real world cases. In 2025, Diana, Ravana, SGD, and other researchers include two-tier assembly accumulation process for capturing versatile factors for legal outcomes. But they also lack semantic understanding in the judicial cases. Usage of AI is being done in different countries. We can see in UK, HART, harm assessment risk tool is being implemented for the organizing individuals on the basis of low, medium, and high risk of committing a future offense. In Estonia, robotic judges for the arbitration small disputes of less than European 7,000. And in US, Compass correctional offender management profiling for alternative sanctions is being used for the evaluation of the offenders. But in that, recidivism risk is very high. In Brazil, Victor is being used in Brazilian courts for preliminary analysis of cases. In Argentina and Colombia, Prometea is being used for forecasting the outcomes of cases. In Chicago, SSL, that is strategic subject lists, are being used for predicting individuals who are likely to be involved in gun violence crimes. In Singapore, real-time speech transcription systems have been evolved and replacing the traditional labor-intensive process. Dataset description in my research has been taken from Bhaumik and Dev Data Lab, which includes datasets from 2010 to 2018 and containing more than 77 million cases. Research methodology. Main research after the case prioritization using Q-learning, fraud detection is being done and various performance matrices has been measured. In these performance matrices, we evaluated the performance of the Q-learning, and then applying alarming systems, we can get uh, quick results to the stakeholders. Techniques here used are Q-learning for the fraud detection, which is not common in legal space, and isolation forest algorithm is used for anomaly detection. For example, in anomaly detection, number of hearings are if more, isolation forest algorithm will soon tell it. Finally, an automated alarming system is being used for notifying the judges, lawyers, and plaintiffs in the case update cases, which shows the transparency and the efficiency of the system. Case studies here taken are the AI assisted robbery case investigation and surge in robbery cases causing judicial backlogs. And using anomaly detection, using isolation forest, flagging is being done, and random forest classifies the likelihood of the criminal involvement. So research findings here, our model accuracy is 0.972, that is 97.2 percentage, precision is 76.3 percentage, recall is 81.3%, and F1 scores is 84.1, which is much higher than the decision bagging, X boost, etc. Conclusion: real-time alarm systems will help in more transparency and improved efficiency, consistency, fairness, and faster decision making in judicial process. Also, in future, better case management would be done, reducing case backlogs and promoting transparencies. These are the references. Thank you. Any questions, please?
It seems there are no questions. Thank you so much, Sayyad, for your insightful and valuable presentation. Now, I'd like to move forward by calling upon our next author, Suchitra, to present her paper on smart rack for drug-drug interaction analysis. You may start by presenting your screen. It seems that Suchitra is
Ma'am,
absent at.
I'm here.
Okay.
Yeah,
You may start with your presentation.
is my screen visible, ma'am?
No, your screen is not visible.
Okay, just now.
Yes, you're visible now.
Okay.
Are
So
you
good
presenting
afternoon.
on behalf of Suchitra?
Yes, yes,
Okay,
ma'am.
okay. Okay, please move.
Yes, good afternoon, everyone. I'm Dhanisha Singh, and I'm representing SRM Institute of Science and Technology, and I will be presenting a research paper today on behalf of Suchitra ma'am, who is unable to attend the conference. So our topic is smart drug for drug-drug interaction analysis. More, in our second slide, the clinicians today face growing complexity, like more drugs, more literature, less time to decide. Medication errors remain a leading cause of preventable harm. especially under polypharmacy. Large language models could help, but they hallucinate, they generate fluent, confident, and sometimes they can be fabricated medical claims, which is dangerous in clinical setting. So our solution is to separate retrieval, safety enforcements, and generation into distinct audible stages so nothing reaches a clinician unless it's grounded in verified evidence. So for the result under 1% of hallucination and 100% safety refusal accuracy on adversarial queries, which is versus 18% and 20% for a naive RAG baseline. In our next slide, we will be discussing about where our existing approaches fall short. Existing approaches that fall short are based on the rule-based clinical decision support systems, which does not scale well as medical knowledge evolves. LLM in healthcare things like BioBird, Clinical Bird, MedPalm, they are fluent, but they can hallucinate. Whereas the naive rack system ground responses in retrieval but still lack explicit safety awareness, so they can comply with dangerous requests. What our system does is that it closes that gap by embedding deterministic safety enforcements directly into the retrieval generation pipeline. In our architectural diagram, we can rest on the four principles which are presented here, which is safety enforcements, which must be deterministic but not probabilistic. Every output needs verifiable evidence. The system must scale across biomedical corpora and it must stay interpretable so clinicians can trace exactly why the system said what it said. These four principles shape every design decision that follows through it. In our system architecture, the architecture has two pipelines here. One is offline, the other is online. And offline, we build a FAISS vector index from a corpus which combines drug bank, PubMed, abstracts, FDA safety documentation, and home medication safety reports, which are embedded with a PubMed BERT style sentence transformer. Whereas in online interface pipeline, a clinician query is encoded with a mini LM query encoder and relevant passages are retrieved from their index. Critically, we can also say that the retrieved documents never go straight to the LLM. They pass through a deterministic safety middleware gatekeeper first so that the retrieval error can never be silently turned into an unsafe answer. There are 10 stage system safety for our pipeline here. That safety enforcement is a structured input and normalization through intent screening for unsafe requests, query decomposition, high recall retrieval, deterministic safety filtering, cross encoder re ranking, severity aberration, evidence bound generation, and final output validation. Each stage is a separate auditable checkpoint. So when something goes wrong, we know exactly which stage we have to look into. In our next slide, the safety middleware decision, it goes, the decision gate is the action basically here. For the unsafe intents, dosage requests, autonomous diagnosis, medication misuse, which are blocked before generation ever happens. Search and safe queries proceed through retrieval, re-ranking, and severity aberration. High severity interactions can get escalated as alerts. When evidence is sufficient, the system generates an evidence bound response, and also when the system or the evidence can be weak or contradictory. It explicitly states uncertainty rather than guessing. Every one of the 10 adversarial queries in our evaluation set was correctly rejected, 100% safety refusal accuracy with it. In this data set, we can talk about that we have evaluated on 50 clinically motivated questions, 20 known severe interactions, 20 safe combinations, and 10 unsafe or adversarial queries, with the ground truth from drug bank, which is verified against public biomedical references. We measured precision, recall, hallucination rate, safety refusal accuracy, and latency, because in the clinical decision support system, safety matters more than the raw speed. How we can compare it is in our system where qualitatively, our system compares favorably to both baselines, basically. A standalone LLM and which has a high hallucination risk, weak safety control, and no evidence traceability, whereas naive RAG has a moderate risk which improves things somewhat, but safety control stays limited and traceability, which remains partial. What our system achieves and gives is a very low hallucination risk, strong safety control, and full evidence traceability by design, not by chance. And our quantitative results, we can say that the results speaks for themselves here, whereas the precision jumps from 0.65 to 0.96, which can recall and improves from 0.82 to 0.89 hallucination, which drops from 18% to under 1%. And safety refusal accuracy goes from 20% to a perfect 100%. The cost is latency, 1.1228 seconds here, which is driven mainly by LLM inference and FAISS retrieval. In clinical setting, an extra second and a half is a small price for near zero hallucination. So that trade-off is calculated here. In our research paper, these are the findings and limitations, which is based on the qualitative behavior. The standalone LLM generate unsupported statements with no retrieval grounding, while our system consistently expressed uncertainty or refused rather than speculating, validated through a two-stage manual check against drug bank and FDA references, which said that we have real limitations also, that is, the knowledge base needs regular re-ingestion to stay current. We haven't yet run prospective clinical studies, which has added the safety pipeline, does increase latency, which could matter in emergencies. So I would like to conclude now. So that the deterministic evidence bound safety enforcement, which can make the generative AI viable for clinical decision support, which is near zero hallucination, perfect adversarial refusal, and high precision on drug interaction detection. That is, the future works means the expanding the medical knowledge scope, optimizing adaptive retrieval, integrating continuously updated healthcare sources, and running real world clinical validation. To be clear about the scope, this system is built for clinical decision support only, not independent diagnosis, prescription writing, or unsupervised patient use. Safety first design isn't a constraint on generative AI in healthcare. It is what which makes it deployable. Thank you. Any questions?
I don't think anyone has any questions. Thank you, Dhanisha, for such an informative and engaging presentation.
Thank you.
Welcome. Now, I would like to move forward. I'd like to invite Vikas Kumar to present his paper on smart prompt adaptive input level optimization with semantic caching and compression for efficient local LLM interference. You may start with your presentation.
So the PPT is visible or not?
Yes, your screen is visible.
Okay. Good afternoon, everyone. First of all, I would like to thank the organizers of ICT4SD 2026 for giving me this opportunity for present our research work. My name is Vikas Kumar and I am from Department of Computer Engineering, Army Institute of Technology, Pune. Today, I will be presenting our paper titled Smart Prompt Adaptive Input Level Optimization with Semantic Caching and Compression for Efficient Local LLM Inference. This work has been carried out under the guidance of Mr. Piyusha Vevhari and Professor Sunil Dhori sir. So, now we will discuss motivation. In recent years, running large language models locally using frameworks like Olama has become increasingly popular because it provides pretty privacy, offline execution, and no API cost. However, even though the models run locally, user still experiences noticeable delay before the model starts generating an answer. There are four main reasons for this. First is every prompt is processed in exactly the same way, whether it is a short question or a long research query. Second, long prompts are naturally contain more tokens, so the model spends more time processing them before generating the first output token. Third is even if a user asks the same question again or asks a very similar question, the model performs the complete inference again instead of reusing the earlier answer. Finally, during long conversations, the chat history keeps increasingly continuously, which makes every new request slower than the previous one. So these are basically the problems. Next, we will discuss about these problems. Existing local inference frameworks like Olama are excellent at serving large language models, but they mainly focus on the inference stages. They do not perform any intelligent processing at input level. Especially, they do not reuse responses for repeated queries. They do not optimize or compress prompts before inferences. Because of these limitations, the system performs unnecessary computation, which increases the time to generate first token or TTFT and reduces the responsiveness of conversational systems. Now, we come to the directly to the solution, which is basically end-to-end pipeline. So in this, we have smartphone consists of 6 coordinated components. Each of components has special responsibility. So everything starts with the user's prompt. The prompt analyzer first counts the token and identifies the prompt type based on these values. The three-path router selects one of the three execution paths. If the prompt is very short, it directly follows the direct path. If it is a medium length prompt, smart prompt basically performs a semantic similarity search, which is basically cosine similarity score threshold is 0.82. At this stage, there are two possibilities. If a cache hit occurs, the store response is immediately retrieved and given to the user. Instead of invoking the LLM again, this response is passed to the conversational context manager where the conversation history is updated and conversation state is maintained. Since the answer is already available, no Olama inference is required. If a cache miss occurs, the prompt is sent to the adaptive compressor. Similarly, all long prompts directly enter through the adaptive compressor. After compression, the prompt reaches the conversation context manager. This component retrieves previous conversation history, builds the final context-aware prompt, summarizes old history. If it exceeds the threshold tokens, and updates the conversation memory accordingly. The optimized prompt is then forwarded to the Olama for inference. After inference, the generated response is streamed back to the user. The important thing to notice is that only cache hit requests completely bypass LLM inference, whereas all other requests eventually reach to the language model after appropriate optimization. So next is these are the experimental setups. We uses CPU-based inference, local inference engine. Basically, targeted language model is Llama 3, which is 8 billion parameter model. five prompt categories we uses here, which is factual, technical, reasoning, code, and long context reg based. And TTFT measurement is basically the uh, evaluation criteria we uses. These are basically the experimental results, and final results are basically these. So in this slide summarizes that main outcomes of the experimental evaluation. The first and most impressive result is the 99.5% latency reduction for cache hit request by reusing previously generated responses. Smart prompt eliminates unnecessary inference for repeated or semantically similar prompts. The second result is 52.4% token reduction for long context prompt using LLM link 2. Reducing the number of input tokens directly lowers the computational workload before inference. During our experiment, the semantic cache achieved a 37.5% cache hit rate, indicating that many users' queries can be answered instantly without invoking the LLM. We also evaluated the conversational context manager by the sixth conversational turn. It successfully reduces the conversation history from 3091 tokens to 481 tokens, representing an 84.4 reduction. Finally, even the cache miss request smart prompt achieved an average of 2.3 improvement percent of improvement in time to generate first token compared to the baseline Olama systems. Next is basically these are the comparison of time to generate first token in Olama baseline models and the smart prompt model. And the cache hit versus miss is basically in smart prompt, it will directly 100 to 200 x faster on repeated and semantically same queries. Comparison with related work. So previously many works are carried out like mean cache or similar approaches mainly provide semantic caching, and some context management always provided context management, but not all these things like prompt compression, semantic caching, context management, three path routing, all these are not provided in single system. A smart prompt basically provide all these things in similar and single pipeline, middleware pipeline, which automatically increase the performance of the local language models and decrease the latency of the system. So these are the future works and contributions. And finally, thank you very much for your attention. I would now be happy to answer any question, if any.
Thank you so much, Vikas, for such an excellent presentation. I think no one has any questions for you. Then we'll be moving forward.
Okay.
Now, I'd like to invite Viraj Surve to present his paper on visual simulators and learning tools for operating system algorithms. You may start presenting your screen.
Yes. Hello.
Yes, you're audible.
Okay. We'll share my screen. Uh, is my screen visible?
Yes, your screen is visible.
Okay. Hello everyone. I am Viraj Ramesh Surve, and today I will be presenting our research on visual simulators and learning tools for operating system algorithms. This work was co-authored by my colleagues Varadna Shikkar and Dhananjay Boob under the guidance of Professor V.V. Vaijapurkar, and we are from Pune Institute of Computer Technology, Pune. Uh, as we know, the operating system, it is a software that manages important computing resources such as CPU, memory, storage. Entire OS is divided into modules such as CPU scheduling, memory management, and disk scheduling. Each of these modules has its own algorithms. These algorithms operate at kernel level and are time dependent. abstract, difficult to visualize just by reading the theory from the textbook and static diagrams. This gap motivates us the need of visual simulators in the OS studies. We perform a systematic review of 36 research papers related to operating system published between 1996 to 2025. We compare them based on algorithm coverage. It means which module does the simulator cover out of CPU scheduling, memory management, and disk scheduling. Second parameter is visualization depth. It means whether the simulator provides static output or animated output. Third parameter was platform support. It means the software was developed for desktop or web. Fourth parameter was empirical evaluation. It means whether the classroom-based validation was performed to check the simulator performance. Based on this, we found that 80.56% of the tools they support CPU scheduling, 36.11% support memory management or paging, and 13.89 support disk scheduling. This indicates that there is no system that covers all of them, and most of them focus on CPU scheduling. 63.89% support animation, and still there is a large portion that provides static output. 27.78% they are web based and can be accessed from any device. Rest of them they use desktop, but they are desktop based, and like some of them are using deprecated technologies. 36.11% include formal educational evaluation, which is still less in number. So based on this, we will see some important graphs. For the first graph, it shows this first graph. It shows the year versus number of publication. We can see the trend that as the need of computer science education grew over the years, the need of OS simulator has also increased. Second graph shows the platform types versus the number of publication. We can see the desktop based simulator have the highest number, followed by web and mobile. Third graph is the OS subscriptions versus the number of studies. We can see the CPU scheduling has the highest number and very few support memory and disks. The fourth graph shows feature score versus the number of studies. So feature score as are the 6 points, these 6 points that CPU, whether the simulator supports CPU scheduling, memory management, disk scheduling, whether it supports animation or not, whether it is desktop based or web based, and whether the formal education evaluation was conducted or not. So based on this, we have plotted this graph, and it shows that most of the system they cover like 4 parameters only, and none of the system that covers all of them. To address these gaps we just saw in data, we designed a 4-layer reference framework for future educational simulators. Our analysis show that none of the existing tools meet all of these requirements as of today. So the first layer is unified subsystem engine. It ensures that the CPU, memory, disk algorithms are treated with equal depth, and the system should be modular such that any in future any of the new modules can be added easily. Second layer is the second layer is real-time visualization. It ensures that the animations are step by step and controllable. Layer 3 is web-based accessibility, ensuring platform independence. Layer 4 is evaluation, ensuring some kind of testing, whether in classroom or through feedback, is performed to improve the system performance. Now, to validate this framework, we developed a functional prototype using C++ and Unreal Engine, which solves the gaps we just identified. Here is a demonstration video of it. I will please let me know whether the audio is clear. To
Viraj,
conclude, yes.
no, you can continue.
Yes. So to conclude, in this research, we systematically reviewed 36 of these simulators, revealing a significant gap in algorithm coverage, visualization depth, platform support, and educational validation. To address this issue, we propose a four-level reference framework and validated it by developing an Unreal Engine 5 prototype that successfully demonstrates CPU scheduling module. Yes, that's it. Thank you. Uh, any any questions?
Thank you, Viraj. I don't think there are any questions. Thank you so much for your presentation. Uh, Now we'll be moving forward to the end of this session. I would like to sincerely thank our authors for their excellent presentations and contribution in this session, and for all our participants for being a part of this international conference. I hope this session was informative enough. On behalf of the whole team, thank you for the support during this 11th version and all the 10 previous versions of the conference. We will be happy to have you in the 12th version in 2027. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the team of ICT4SD 2026. I would like to also thank our session chair, Kirit Modi, for chairing the session. Now, as a token of appreciation, I would like to share the certificate on behalf of the team. This token of appreciation is on behalf of Team ICT4SD 2026 and Global Knowledge Research Foundation and partners. I would like to extend my sincere gratitude to everyone present here. Now, I kindly request you all to switch on the cameras for a quick snapshot of the virtual conference.
Yeah, so ma'am, I would like to say something. Yeah, it was really wonderful, I can say, sessions, all the sessions which I have attended. And I hope that next time all the authors they come with some more the innovative work in the concerned domain, whatever they presented today. And all these sessions were very informative and fruitful. So I again congratulate to all the authors who participated and presented their innovative work. Yeah, thank you.
Thank you so much, sir. Thank you, everyone, for attending the session. Stay safe, stay healthy. Bye.